Hi, in this video, we're going to look at the rate law. In chemistry, the speed of a reaction. So think of a reaction that you're familiar with. It could be something like burning a match, right? Think about how fast that happens. Probably only about maybe 5 to 10 seconds after you strike the match, it starts to burn the wood, right? All of the sulfur and phosphorus mixture on the tip of the match is gone after 5 to 10 seconds. So that's a relatively fast reaction. The terminology that we use to talk about how fast a reaction is the rate of the reaction. So rate is essentially speed, okay? The rate of a reaction is typically done in the units of concentration divided by time. So for example, 3 moles per liter per second, right? That's a concentration divided by a time. It can also be done in pressure units per time. So for example, atmospheres per second. Now, it doesn't have to be per second. It could be per minute or per hour or per year, but most commonly it's per second, okay? So in this particular problem, we're going to look at what's called a rate law. In a rate law, it typically says rate, the speed of the reaction, is equal to K, lowercase k, right? Small k. K is called the rate constant. Then you have in brackets the reactants. So we don't see the balanced equation here. We don't know what the balanced equation is, although we could surmise it. This rate law says that the speed of the reaction is equal to the rate constant K times the concentration of N2. Now, N2 is nitrogen. That's the nitrogen that when we breathe goes into our lungs from the atmosphere. N2 times the concentration of H2, hydrogen gas, squared. Okay, this is the form of a rate law. It's equal to K times the concentration of each of the reactants raised to either the first power or the second power, maybe the third, maybe a half even, but most commonly 1 or 2. So N2 is to the first power and H2 is the second power. This particular question is all about terminology, or at least for the most part, it's about terminology. The last couple parts ask you to do some simple calculations. So let's take a look at this one. Let me stop share here, and I'm going to bring up the whiteboard so we can take a look at this particular problem. Okay. So in this, we're told that the rate is equal to K times N2 times H2 squared. Okay. And then we're asked several questions. So the first question we're asked is the reaction order in N2. And then we're asked essentially the same thing, the reaction order, but this time in H2. And then the overall reaction order. Okay, relatively simple. So here's the way this works. Even though we don't write it, there's really a 1 there, right? And so the reaction order is merely the exponent. It's the power that you're raising that concentration to. So for this, it would just be 1. For H2, the exponent is explicitly written as a 2. And then for the overall, you just add them together. 1 plus 2 equals 3. Okay, those are called reaction orders. So overall, we would actually, in words, we would say this is third order. we would say this is second order. And then we would say this is first order. Okay, so for the overall, you just add the exponents together. If there were 3 reactants, then you would just add those 3 exponents together. Okay, the significance of this is that what happens is the larger this number is, the bigger the effect on the rate, right? So if I put if this is a 2 squared, second order, changing this number here has a bigger effect on the rate than changing this number here by the same amount, because that's only a 1, right? The bigger exponent has a bigger effect on the equation. You know, you can think of it sort of graphically. If you have a linear equation, it might look like this. So this is, you know, y equals x to the first power, right? That's an exponent 1. But suppose we do second power. It goes up like that, right? Here's y equals x squared, right? So bigger effect, bigger changes occurring when the exponent is larger, okay? Now, I'm going to go ahead and stop that share, and we'll come back to our question so we can look at the last couple parts. Okay, now we get to some calculations. At a certain concentration of N2 and H2, the initial rate of the reaction is 3.0 times 10 to the 4 molarity per second, right? Moles per liter is molarity. So that's molarity per second. That's concentration units over time units. What would the initial rate of the reaction be if the concentration of N2 were halved? Round your answer to 2 significant digits. If it were halved, we want to know what the initial rate would be, okay? So for this one, we have to do a little bit of thinking. So I'm going to put the rate up again, the rate law. Okay. So what they say is that initially the rate is 3.0 times 10 to the 4th molarity per second. Then the concentration, so that's the first situation, then the concentration of N2 is halved. What happens to the initial rate? Okay. So let's take a look at that one. There's different ways in which you can approach this problem. One way to approach this problem is just to actually put numbers in. So where the case is where the rate is 3.0 times 10 to the 4th molarity per second, you could just go ahead and put in a number for each of them, for everything. So suppose I put in 1 for K, and suppose I put in 1 for the concentration of N2, and then I put in 1 for the concentration of H2. I'm just putting in numbers. I made the number up. Well, that would just be 1, right? Now what I'm going to do is I'm just going to change one thing. I'm going to put in 1 for K. Now I'm going to have N2. That means you make it a half, right? And then I'm going to keep this the same. So they didn't say to change anything else. They just say change N2 to 1/2 of what it originally was. Well, this is a half, right? So look what happened. By having the concentration of N2, the rate of the reaction has also been halved, okay? So now, if the rate over here was 3 times 10, and actually, I'm sorry, it was 3.0. I just want to make sure we get the significant figures. If the rate is 3.0 times 10 to the 4 molarity per second, and now we're saying the rate is half of what it initially was. Well, the rate for this one would be 1/2 times 3.0 times 10 to the 4 molarity per second. So that would be 1.5 times 10 to the 4 molarity per second. Okay. Now I picked 1 to put the number in. for all of those concentrations and the rate constant, you don't have to put 1, you could put a different number in. There's actually a different way to do it. So I'm going to show you a different way to do this. And sometimes this can be confusing for students to see that there are multiple ways of doing the same thing, but it is something we can do. So here's what I'm going to do. I'm going to say that we have our initial rate here, 3.0. So this is method 2. In fact, let me go ahead and write this down. Method 2. We have the rate is 3.0 times 10 to the 4 molarity per second. That is equal to the rate constant times the concentration of N2 times the concentration of H2 squared. Now, I'm going to make a ratio. So what I'm going to do is I'm going to say that is now divided by our initial rate that we want to find out. Case 2 over here. That would be equal to this ratio, K times 1/2 times the concentration of N2, 1/2 of what it originally was, times the concentration of H2 squared. And actually, I should go ahead and make those square brackets. 1/2. There we go. So I did a ratio. I took the initial rate, which was given, 3 times 10 to the 4th molarity per second, divided by the rate that we want to figure out. That would be equal to the ratio of the rate laws. The rate law initially divided by the rate law once we've halved the concentration of N2. And look what happens on the right side. K over K is 1. H2 squared over H2 squared. That's 1. N2 over N2. So what are we left with? We're left with 1/2. Interesting, right? So now 3.0 times 10 to the 4 molarity per second over the rate that we're trying to find out is equal to 1/1/2. Well, that's an easy calculation to do. 1/2 is 2. So that's 2. So now we have 3.0 times 10 to the 4 molarity per second over the rate that we want is equal to 2. Well, we don't want to know that this is 2. What we want to know is what that rate would be. So what we can do is just multiply both sides by rate. So I'll bring that up here. If you multiply both sides by rate, okay, then to find the rate, we divide by 2. And that would give us our rate. And that would be 1.5 times 10 to the 4 molarity per second. Same answer as we got with the first method. So these are 2 approaches. The second approach, there is a validity to that. The only problem with the first approach is that putting in numbers in some problems could be poor assumptions. But for this type of problem, it should be fine. So either approach is good. Okay. So that's the 4th part of the question. The 5th part of the question is now we're going to try to figure out what the value of the rate constant is based on some given numbers. So let me stop share this one and bring that question back up. Okay, so in the last part, I'll call it part 5, the rate of the reaction is measured to be 12.0 molarity per second when the concentration of N2 is 0.35 molar and the concentration of H2 is 1.0 molar. Calculate the value of the rate constant and round your answer to 2 significant digits. Notice they give you the units here. They just want the number here. Also notice the units are reciprocal molarity squared reciprocal seconds. Okay, so you just need to get the number there. So let's take a look at this one. This one is actually just a little bit of algebra and just calculating it. Not that difficult. Okay, so let me put the numbers down. We're told that the rate is 12.0 molarity per second. we're told the concentration of N2 is 0.35 molar. And we're told that the concentration of H2 is 1.0 molar. And then we're asked to find the rate constant. And then we're told the units are reciprocal molar squared times reciprocal seconds. Okay. Well, I'm going to come back to the rate law. Rate equals K times the concentration of N2 times the concentration of H2 squared. Okay. We want to find the rate constant. Well, let's just do the algebra first. We want to isolate K. So if I divide both sides by N2, for this one, I'm actually doing it explicit. I'm going to do it really step by step just to show you how to get about this. N2 over N2 is 1. So now you have, I'm going to write it again just so that you can see it clearly. Okay, and there's a K here, sorry. Now in the next step, I'm going to divide both sides by H squared. So rate divided by N2, concentration of H2 squared. Okay, the way we say that is concentration of H2 squared. The brackets are concentration of. So now that would be K times concentration of H2 squared over H2 squared. Concentration of H2 squared, sorry. So that becomes 1, and you just got K here. Okay, so all you need is the rate, 12.0 molarity per second, divided by concentration of N2, which is 0.35, divided by the concentration of H2, which is 1.0 squared, and that's equal to K. All right, so now, I forgot the units. Okay, so now all we have to do is plug those numbers in and we should be okay. So 12 divided by 0.35 divided by 1.0 squared, well, that just comes out to 34. 2 significant digits. We'll put a decimal point on the right just to indicate that that's where the decimal is. And then look what happens to the units. You have a molarity here, but it cancels with that one. And then you have 1 over seconds. So, you know, I'm going to write this as seconds to the minus 1. Seconds to the minus 1 is just the same as 1 over seconds because we have 1 over seconds here. These 2 molarities cancel, but you've got these 2 molarities here. So you really have 1 over molarity squared. Well, that's written as m to the minus 2. Okay, so m to the minus 2. It is customary to put the molarity first and then the time units second. And there's your K. All right, around 34. It's a little bit more than that, but they stayed around it to 2 significant digits. Okay, so there you go. That is using the rate law. Relatively straightforward.